Thank you for joining today's Beyond the Basics webinar, Identifying and Mitigating Runout. My name is John Kingham, and I will be your moderator for today's session. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your screen are multiple application engagement tools that you can use. All the engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can make a request to book a meeting or a demo directly from your console. Just click on the appropriate engagement tool and add your information. For the webinar portion, the slide area can be maximized to full screen by clicking on the arrows in the top right corner. If you have any questions during the webinar, please submit them through the Q&A engagement tool at any time throughout the presentation. We will try to answer these during our Q&A session, but if a fuller answer is needed or we run out of time, it will be answered later via email. Please know that we do capture all questions. I want to remind everyone that this webinar is just one in a series of planned webinars. If you have missed one or two, no worries. The related content engagement link in today's webinar can direct you to our on-demand site. While you are there, you can also download a copy of today's slide deck and link out to sign up for future sessions in the series. We would also like to ask you to take a few minutes at the conclusion of the webinar to complete our survey. This will help us bring more topics and improve on future webinars. The proximity probe offers many advantages over the shaft rider technology that it displaced. No pun intended. Well, maybe there was. It does have one drawback, however, and that's Runout. In this short course, learn what Runout is, how to measure it both at the machine shop and in the machine. Learn how to prevent issues when sending your rotor out for machining. And finally, learn how to properly use runout compensation. During today's webinar, Derek Prinsloo will be our instructor. Over the course of the last 20+ years, Derek's career in Bentley, Nevada has ranged from generating proposals to helping customers in the field as a machinery diagnostic engineer. Based out of Toronto, Canada, Derek is currently the team leader for the application and solution architects in North America. As the technical experts for the sales team, the ASAs need to be knowledgeable about the entire Bentley, Nevada product line, from probes to monitors to condition monitoring and diagnostic software. With that, I'd like to turn things over to Derek.
Thanks, John. Through the course of this webinar, we'll discuss what Runout is, how it is defined, how it is created, and then we'll move into different ways that it can be measured and some of the considerations when you need to quantify it. And finally, we'll review what some of the next steps are. Does it need to be fixed? Do you just need to account for it in your diagnostics? Can you cancel it out? But before we can think about measuring it or fixing it, we first need to be able to define it. We typically define Runout as the error between the actual and indicated target position. In the context we'll be discussing today, that target is primarily going to be a shaft rotor, and more specifically, the shaft surface that's being observed by the radially mounted proximity transducers. It's important to remember that runout is usually going to be caused by a combination of mechanical and electrical faults in the target surface. The combination of these effects is what we refer to as total indicated runout. And what do we mean by mechanical and electrical runout? Well, mechanical runout is a measure of the shaft's deviation from a perfectly uniform radius. This could manifest as a non-uniform overall shape, like an oval or flat spots, or it could be more acute in nature, like a scratch or a dent. Electrical runout is a measure of the shaft's electrical property variations. This is less obvious. You're unlikely to be able to see it from a visual inspection. We'll need more specialized tools to detect this. We'll discuss how that happens soon. Now let's talk about some of the sources of runout. From the mechanical side of things, the machining process is one of the places where you might see some defects being introduced. This could be if the bearings of the lathe are not good, if the lathe wasn't quite centered on the shaft, if the tools weren't sharp, or if the operator wasn't experienced. There's any number of things that could be introduced from a machining process aspect. Another very typical thing that we see is the dents from handling. This could be scratches, dents, burrs, pipe wrench marks, etc. The picture here shows one example where it appears that a pipe wrench was used to turn the rotor over. So taking care in terms of how things are transported and how things are handled, it will definitely help to reduce some of this. Rust patches, again, this is more from a transportation aspect. If care isn't taken in terms of how things are supported and how things are protected from the elements. Rotor bow is another aspect of mechanical runouts. In this case, the rotor is left unsupported for too long, and it actually bows, and this will result in some run out there as well. And finally, defective and worn bearings in the machine and lathe supports. This kind of circles back to that initial machining process aspect, but is definitely something to keep an eye on. From the electrical side of things can get a little more complicated. Things to do with the metallurgy, how the thing was forged, heat treatment, the grinding, if grinding is too intense in one spot or another, magnetism, stress effects, the handling and plating. All of these things can affect the actual material of the shaft and will affect the electrical properties or how that electrical runout occurs in the shaft. Before we go any further, it's important to do a quick review of the technology that most of us will use to measure and detect runout, the proximity probe. Most eddy current displacement sensors work on the following principle. A current goes through the eddy current sensor coil and generates a high-frequency electromagnetic field. This magnetic field interacts with a metal target and produces a signal we can measure. The signal from an eddy current proximity probe is both a function of the gap between the probe tip and the target material, and it's also a function of the electrical conductivity and magnetic permeability of the target material. In other words, a proximity probe not only measures the shaft surface properties, but also responds to the shaft's material properties. If you think back to a moment ago, the combination of mechanical and electrical runout is called total indicated runout. That's right. The prox probe measures TIR. This is important to understand when utilizing prox probes in a monitoring and protection system, and highlights the importance of understanding and mitigating runout. Proximity probes are very accurate and very detailed, but as such, they'll also pick up any inconsistencies. So care in the preparation of the shaft is of the utmost importance. And when we take two proximity probes, position them 90 degrees apart in an XY configuration, we're now able to measure a couple of things. From an average standpoint, we're able to see where the shaft is within that bearing. And on a more instantaneous point, we're able to see the movement of that shaft in terms of vibration. So when we're describing those things, we're not describing the shaft as a whole. Really, we're looking to describe the path of the shaft center line. And of course, since we can't directly measure the shaft center line, we need to take measurements on the shaft surface and make some inferences based on those measurements. The assumptions that we make when we do that sort of thing is that the shaft is perfectly round and that there are no surface imperfections. This is, of course, not reality, and that's why we need to consider runout. And when we look at the path of the shaft center line, also known as the orbit, we look at it typically in two different conditions, at slow speed and at high speed. At slow speed, we make a couple of assumptions, that there are no dynamic forces acting on the shaft, that the shaft is just rotating about its center line. And when the shaft surface and everything looks good, ideally what we'll see is just a dot like we see here. At higher speeds, the shaft is rotating very quickly, and we're going to have those dynamic forces acting on the shaft, which then give us the vibration. And if the shaft surface is relatively clean, we're going to get a nice oval-shaped orbit, something like we see here on the left. However, if the shaft surface is not clean and we have runout, then at low speeds, we're going to see some interesting things like we do on the right-hand side here. And when you add vibration to that, those messy things get even more messy and make our diagnostics unreliable. When we look at vibration, we want to be able to see the vibration. We don't want to have all this other noise in the way. And that's why runout is important to measure and to mitigate. Next, look at how we go about identifying different types of runout. In order to understand what bad looks like, we also need to be able to understand what it looks like. So first we'll start with the simplest of simple scenarios. In this case, the shaft is operating at slow roll, and the shaft is perfect. So what we mean by perfect is the shaft is perfectly round, there are no surface imperfections, and because of that slow roll, there are no dynamic forces. I know this is wishful thinking, but let's just take it as an example. The signal from each of those X and Y proximity probes would look something like we see on the bottom left. It would just be a simple straight line, and with a key phasor reference point, you would see a little blip at each key phasor mark. But otherwise, you'd see no signal. Now let's take our perfect scenario and run it up to full speed. In this case, the shaft is still perfectly round, there's still no imperfections, but now we have the dynamic forces of vibration introduced. Yes, this is still wishful thinking, but it helps to serve as an illustration. In this case now, we're going to have what a perfect shaft looks like when it's vibrating nicely, perfect sine waves. And once again, you'll note the key phasor marks happening once every revolution. And in this case, it's primarily 1x vibration, so we see one cycle of vibration for every one rotation. So now what happens if the shaft is not perfectly circular? In this particular example, the shaft is more of an oval shape. And looking at it here in this example at slow roll. So although there's no dynamic vibration and there's nothing else going on there, the shaft surface is smooth, the shape of the shaft is not circular. So what we see now is we see two cycles of quote-unquote vibration for every one rotation. Of course, we know because it's at slow roll, there's vibration going on. So we're getting an unnatural, not necessary signal in there. If we were to ramp this shaft up to full speed, you would see that 2x component overlaid on top of the actual vibration happening in the shaft itself as well, which would then, of course, obscure the diagnostics that we're looking to do. If somebody came and looked at this signal at full speed and saw a high x, they might jump to some other conclusions if they didn't realize that the shaft itself was out of round. In another example here, the shaft is perfectly round, but the shaft surface is not perfect. We've introduced one little scratch in that shaft. And so what does that look like? At slow roll, again, there's not going to be any vibration there, so it's going to be a straight line. But at regular intervals, you're going to see a little blip in what should be the vibration signal. You're going to see a little blip there as a result of the scratch that those probes are seeing. Some of the characteristics of this that you'll notice, if you're comparing X and Y probes, is that you'll see that same size scratch, so it'll be the same, typically roughly the same depth, but they'll be 90 degrees apart from each other, because the Y, if it's going clockwise, first the Y probe will see the scratch, and then the X probe will see the scratch. So this is showing that that they'll 90 degrees apart. And now if we perfectly circular shaft up to full speed and add some vibration to it, we see that nice sine wave that we noticed before, but overlaid on that sine wave, our little scratch mark there. And the mark is still in the same location. So the phase relative to the key phasor doesn't change because that scratch is in a fixed position. It's still going to be 90 degrees apart from each other, and then they're still going to be the same distance away from where that key phasor mark fires. As that vibration changes, and as the shaft goes through resonant speed or something like that, how that shaft adds with the vibration can change. So the response to that scratch, or the overall vibration that we see with that scratch introduced, can vary depending on the shaft speed and the shaft condition. So this is where things start to get tricky, and this is where things start to get challenging. The example I just gave is a relatively illustrative example. In that case, the size of the scratch was relatively small compared to the vibration. But in real world, things are a lot more messy. This is one example that we have from the field. In this case, the little mess of signal there in the middle there is a vibration amplitude. And those two legs that you see are actually the scratch that's showing up from on the shaft surface. And in this scenario, the scratch itself is actually 3 to 4 times the amplitude of the vibration itself. So that's significant. If somebody saw that and, this is getting close to an alarm level, the actual vibration itself isn't that bad. The machine is operating quite well, but the total indicated vibration, the combination of the actual vibration plus the noise, plus the runout, that is quite severe. So it can lead to inappropriate or inaccurate machine health decisions and machine maintenance decisions. A couple of things to note when we talk about surface defects on a shaft surface, particularly in the probe track, where the probe is going to be observed. Just as a quick check in the field, if you can see a defect on the shaft surface, chances are the probe will also see it. And if you can touch it, if you can run your fingernail over it and catch it, and you feel that your fingernail catching on the defect, the transducer system will also see it. So just as an initial check, these are a couple of ways to assess whether surface defects are serious or not. And let's take a quick look at electrical runout now. In comparison to what we were looking at before, electrical runout is a result of imperfections in the shaft material, not necessarily the shaft surface. So visually, it may look okay, but the probe itself is going to read it. What does that look like when you look at the X and Y signals? Well, it's going to look very similar to what we saw before. Because it's a material property of the shaft, each probe is individually going to see that noise as it passes by. So the amplitude between the X and the Y probes is going to see that same amplitude of noise between each other, and it's going to be 90 degrees from each other. Here in my example, I've just done a very simple little small patch of quote-unquote electrical runout to show that it's easy to see. But in study, it's going to be a lot harder to identify. Typically, electrical runout or shaft material imperfections are going to be around the circumference of the shaft. It's going to look like noise. Even though the shaft surface may be perfectly smooth, you're going to see that showing up as roughness in that signal. Definitely need to be aware of that. And how do we detect electrical runout? Well, this one can be a little more tricky. Visually, you likely won't see any evidence. If there's a really severe defect in the manufacturing of the shaft, you may see some discoloration or something on the surface. But visually, it's not going to be as obvious as before, where if you get a scratch or you can catch it in your fingernail, you see it. Visually, it's not as obvious. However, the proximity probes will see it. So that is, having the prox probe there is one way to pick up electrical runout. However, proximity probes also detect mechanical runout. So that's where things need to be able to differentiate between the two, and we'll talk about how that happens in a little while here. On the other side of things, there is more specialized electrical instrumentation or general glitch identification or electrical runout identification. We can give you some reference material or reference folks to talk to about that. And this is generally going to be to measure it while it's outside the machine in the machine shop. I wanted to highlight one more here that you may have noticed before, but I wanted to mention it specifically here. When looking to identify or looking for telltale signs of mechanical runouts in their surface defects or scratches, one thing to really keep an eye open for on orbits, you'll see them as little wings or horns sometimes. These are the 90-degree signals as the defect passes by each of the probes. So it'll be roughly the size, and they'll be 90 degrees apart. So you can see that in the bottom orbit there, the shaft is reacting in line with those X probes that are mounted at 45 degrees left and right. It's a little harder to see on the waveform sometimes, but the green markings there show it is degrees apart, and they're roughly the same size. But it gets to be really obvious when you look at the orbit sometimes. I should reiterate that the previous example was done at slow roll. So remember, at slow roll, there's no dynamic effect on itself. It's just the shaft rotation, the pure shaft rotation. So any sort of runout shows up very clearly. This example is that same shaft now running at 3,600 RPM, so running at full speed. You still get a bit of that sense of the pieces happening, or the scratch components at 90 degrees from each other. But now once you add the actual vibration amplitude in there, it gets a little messier, it gets a little trickier to identify. But seeing things at 90 degrees from each other will be your first sort of clue to go back and maybe take a look at some slow roll data and see whether you're dealing with runout in addition to vibration, or whether there's something else going on here. In the following section, we're going to look at some ways of quantifying runout. API 6.7, which covers the repair of special purpose rotors, provides a very detailed description of how to measure runout. In general, API recommends that the shaft be supported in V-blocks, that an eddy current probe system and a mechanical readout are used in conjunction together and are positioned perpendicular to one of the V-block sides. And runout is measured in terms of peak-to-peak probe output. We're going to cover all of these things in much more detail here, but I wanted to give a quick overview of what API 6.8.7 covers. The following couple of slides are going to go through these 7 points in much more detail. We'll talk about V-blocks, why to use them, what are some of the considerations for them, the eddy current probe system, some of the considerations there, why we choose a key phaser, why we utilize a key phaser, and also a mechanical runout indicator like a dial gauge or something. We'll talk about the probe mounts and how they have an effect on measuring runout. We'll talk about the different types of recording and measuring equipment, what we do with the data analysis, and also the magnetic field check. So first, let's talk about the V-blocks. One of the primary reasons that V-blocks are recommended is that the runout measurements should be made in apparatus separate from that in which the machining was actually performed. For example, if a lathe has bearing wear that produces an elliptical shaft cross-section, the shaft will appear perfectly round as long as it's in that particular lathe. So by moving the shaft to a separate measurement environment, for example, V-blocks or maybe a balancing machine, the error induced by the lathe will not be masked, and we'll be able to pick that up. When looking at V-blocks, you want to choose precision V-blocks and ideally have the pads either be hard Teflon pads or have a hard Teflon piece in between the V-block pads and the shaft, and possibly have lubrication there. This helps to keep the shaft from kind of sticking as the shaft is rotated. The other end of the shaft can be mounted in a lathe, for example, where you can rotate the shaft very slowly and keep control of it as it goes around. You want to be able to support the rotor on the journal areas and add lubrication. You don't want to support the rotor in the probe track, as that can induce some noise and can induce other sort of defects in there. So make sure that you're supporting it on the journal areas. And if possible, turning the device should enable a constant speed for about 10 revolutions. So if you're doing with digital or electronic data gathering technologies, it's nice to be able to have a couple of revolutions that way. The other way to do this, or to take measurements, is to have the shaft turned at specific increments. Oftentimes we'll put a piece of tape around the shaft and mark it in 10. Ideally, you want to do at least 10-degree increments around the shaft surface, if not more. And as you turn the shaft for each of those 10-degree increments, you take a new reading and mark that on the sheet, and that's how you get your shaft circumference measurements. If you are able to put it in a lathe and have it rotating at a constant speed, we do like to have that speed to be quite low. So anywhere from a fraction of our RPM to about 20 RPM at the most. You want it to be nice and low and controlled so you can keep an eye on things. And although API 6.8.7 recommends V-blocks, they're not always going to be the best solution for this task. This here is one example that we've seen in the field where the shaft, just due to the machining errors, had a sort of a 3-lobe design. And you can see there that the dial gauge, as the shaft is rotated, just the way the geometry is, the shaft actually showed a straight line. The shaft showed as if it was perfectly circular. But that just happened to be the way the lobes were interacting with the V-blocks as the shaft went around. In this case, being able to mount the shaft or fix the shaft on the shaft center line would have illustrated those lobes. You would see the trace shown there by the green curve underneath, as opposed to just a straight line as it would have showed up in the V blocks. So just be aware of that. If possible, balancing machines will often be able to give you that sort of that fresh reference. And as a quick reminder, not to measure the runout in the same lathe that the machining was done, because any errors induced in that machining will not show up in the runout measurement if you use the same machine. In terms of the actual probe system used to measure runout, it's rarely practical to be able to use the exact same probes that are going to be used in the field. But at the very least, we do recommend that you use at least the same probe series. So from a Bentley Nevada perspective, if 3300 XL probes are going to be used in the field for the XY measurements, we recommend using a 3300 XL probe in the shop as well when doing the runout measurements. As always with proximity probes, make sure that the series between the probe cable, the extension cable, and the proximeter are the same, that the cable lengths between the probe cable and the extension cable match up to the proximeter type. So if you got a 0.5 meter probe cable and a 4.5 meter extension cable, make sure you've got a 5 meter proximeter. All of this leads up to the second point there, verifying the transducer scale factor. So making sure that the system you're using is actually going to give you, for example, with an 8 millimeter probe, it will actually give you 200 millivolts per mil. So one way to do that is to guarantee that all the pieces match up, but then also it's also important to check and confirm that the proximeter that you're using matches the shaft material. As you hopefully know, the standard Bentley Nevada proximeter is calibrated for 4140 steel. If the shaft you're measuring is not 4140 steel, you may get a different probe curve, a different scale factor. So it's important to be aware of this and to confirm that before starting your checks. And finally, as with any electronic instrumentation, make sure to check for any ground loops in it and make sure you're not inducing any other noise in the system so that you're getting the cleanest possible signal from the shaft. If you are able to mount one end of the shaft in a lathe and get a nice, clean, even rotative speed for the runout measurement, that's great. And if you want to do that, ideally we would have a key phaser mark in there as well. This gives you a once per turn indicator so that you can compare over the course of that rotation the shaft runout. If this isn't possible, or if you were just moving the shaft component, angle by angle, a key phaser isn't as critical, but some other marking methodology is very important. So as I mentioned before, if you put a piece of tape around the circumference of the shaft with markings on it, whatever system you use, make sure it's recorded, make sure you got a frame of reference so that if somebody goes back and if they do need to do some sort of reparations on the shaft, that they're able to use your same frame of reference and do the repairs where they need to be done. Next, we also recommend having some sort of mechanical runout indicator. So in addition to the proximity probe, we want to have something like a dial indicator or an LVDT or some sort of modified eddy current probe using a connecting target or contacting target. So we need to be able to measure something physically on the shaft surface to get that purely mechanical runout measurement from the shaft. So while the mechanical indicator is not necessary to measure the total runout, it is useful for tracking the runout origin. So being able to compare the total indicated runout from the eddy current probe and be able to differentiate between what is mechanical and what is electrical. So what do I mean by that? Let's take this one little case example here. So on the left, the shaft is an oval shaped. So from a mechanical standpoint, it has runout. But from an electrical standpoint, it is perfectly fine. The shaft on the right is perfectly round. So from a mechanical standpoint, it's great. But electrically speaking, it's got some runout. Again, this is a purely mathematical example. It'd be difficult to do this in the field, but bear with me here. If we were to measure both of those shafts, if we were to do runout measurements on both of those shafts, the signal that you would get on the right-hand side would look roughly the same. They both show that sort of sinusoidal two cycles per revolution response as a result of what that proximity probe is seeing. So remember, the proximity probe can pick up both mechanical and electrical defects. So those two examples, it's going to look the same. Now, if we were to put a dial indicator on those same two shafts, we get a different result. So for the shaft on the left, which has the mechanical runout, you're going to see a very similar sort of that sinusoidal response. So as those lobes go past the dial indicator, it's going to cycle up and down, and you're going to see that two cycles per revolution showing in the dial indicator. However, the dial indicator on the right-hand shaft is going to show no movement. So it's going to be just a straight line. And when we see a straight line from the dial indicator, we know that that is perfectly circular. So that's why just one or the other is never going to give you the complete picture. Just using proximity probes is going to give you the total indicated runout, but it's not going to help you differentiate between the mechanical and the electrical. Just using dial indicators will tell you what's mechanical, but it's not going to help you differentiate between mechanical and electrical. By having both probes on the machine, that's when you can put the two results together and start to differentiate. So for the shaft on the left, we would see that the dial indicator matches with the eddy current probe, and we can say that yes, whatever the eddy current probe is seeing is confirmed by the dial indicator, so this is purely mechanical. For the probe on the right, we're going to see that the dial indicator does not agree with the eddy current probe. So what the eddy current probe thereby is seeing is purely electrical. So by putting these together and being able to subtract them, we can start to differentiate between what is electrical and what is mechanical noise or runout. How you mount the probes is also an important consideration. Depending on how well equipped the machine shop is that you're using, they may have some very solid probe mounts that you can mount the probes in. But that's not always going to be the case. So you're typically going to have to bring something with you or use something external. Although gooseneck fixtures are very convenient and very easy to set, they are prone to flexing or drooping over time if you're not careful, if you don't tighten them down properly. Therefore, we usually recommend, or we always recommend using a post, if you have to do something temporary, using a post and rod style indicator holders. These you can fix them very tightly. They're going to sit, they're going to remain where you tighten them, and you're going to get very consistent readings turn after turn. Now you've got all the equipment set up and you're ready to actually take data. You want to make sure that when you collect the data, you're able to record the information from both the eddy current probes and the mechanical runout probes together at the same time. The preferred way of doing this is with a digital acquisition device of some sort. Bentley, Nevada, you could use an Audrey, for example. This will be able to, if you get the right instrumentation, you can bring the information in and record that constantly as that shaft is rotated at a constant speed. This gives you a very clear, very finite, very fine resolution picture of what the surface of the shaft looks like. However, we recognize that that's not always the case. So if you do need to do it more manually, make sure that you mark those fixed number of degrees around the shaft surface and do a couple of turns and do a couple of measurements. So at least a couple of rotations to make sure that the readings are consistent and repeatable. Oops, looks like I was getting ahead of myself a little bit. So yes, for data analysis, again, make sure that you're doing several revolutions, making sure that the readings are consistent, and putting in a different way, synchronous with the rotor. So there, when I say that is basically saying that it's repeatable, so that you're seeing the same markings or the same defects or deviations in the same place and the same spot on the rotor as it goes around. If you're seeing changes, if you're seeing different types of readings, you need to go back to the previous couple of steps and do some troubleshooting. Are there any pieces that are moving? Are your Teflon pads shifting? Is the lathe perfectly centered? Are your probes mounted very securely? Are they shifting? Are they mounted? Is the magnet for the post and rod holder, is it mounted on something solid, or is that something shifting as the machine rotates? All of the variables need to be as consistent as possible so that the readings you get are as reliable as possible. And finally, if you've got the equipment, also do a full magnetic field check around the full circumference of the shaft, the whole 360 degrees. When you're recording this, make sure to include the maximum readings, including the positivity sign. So, -2 to +8 or -4 to -1 Gauss. Make sure you record that as accurately as possible. And while I generally like to be a more positive person, there is also value in noting things that you should avoid when doing runout measurements as well. So a couple of things to keep in mind here. Do not measure runout in the machine bearings. You can check for excessive runout. You can identify when you suspect that there's excessive runout, but you can't measure it there because the position of the rotor versus the probe can't be fixed like it can be in a machine shop with precision V-blocks, et cetera, et cetera. Don't use roller supports to support the shaft when doing the measurements, as this can add or subtract from the runout, depending on the shape of the shaft. Don't measure runout directly on the lathe. We've already mentioned this before, but it's worthwhile reiterating because oftentimes we get asked to do this because it's more convenient. The shaft is already mounted there. Hey, why can't we just throw a couple a prox probe and a dial indicator on it? Any eccentricity in the rotor supports can cause mechanical runout that can't be seen when checked in the same support structure. If the rotor support has an egg-shaped travel path due to bearing wear, the rotor will be egg-shaped when it's machined. But because you'll be looking at it in the same machine that machined it, putting a probe there, it's going to look perfectly round. Always have it in a separate machine, either with V-blocks or in a balancing machine, something that is a new measurement reference to make sure that you're getting an accurate measurement there. Don't use improper measuring equipment. Make sure, as we talked about already, make sure the probes are accurate, make sure the probes are matched up, both to themselves in terms of the cable lengths, but also in terms of the shaft material. Make sure that you're getting as much information as possible. As I said, having an electronic measurement device like an Adre is incredibly useful and gives you a lot more information than just doing it a couple of degrees at a time. And don't limit your measurements to a fragment of the path. This sounds a little weird, but really there's some machines where either through thermal growth or just through basic operation, the machine can be expected to travel axially. So the probe path or the target area that the probe is going to be looking at will not just be the width of that probe. It could be a certain amount on either side of that. So if you know that the shaft can potentially move axially, make sure you maybe take a couple of measurements along that full target surface area. Make sure that there are no deviations on either extreme of that probe target path. Well, now that we have very accurately and very precisely measured the runout, how do we know if it's too much? To have an arbitrary reference or to have a neutral comparison here, ISO 7919, the mechanical vibration of non-reciprocating machines, gives us a nice clear recommendation. It is recommended that the total combined electrical mechanical runout, so total indicated runout, the TIR, as measured by the transducer. So again, remembering this is by the proximity probe that's looking at the shaft, should not exceed 25% of the allowable vibration displacement, or 6 micrometers, or equivalent to 0.24 mils, or thousandths of an inch, whichever is greater. So what limits do we use for that assessment? Well, if in the absence of any other recommendations or any other specifications, ISO 7919 gives us a couple of recommendations. For new machines, generally it's specified to use that A-B boundary, the amplitude for new machines, or for older machines or machines that are in use in the field, using that B-C boundary, so from the green, light green to yellow, using those limits. But it's important to recognize that these limits are statistical recommendations based on the variety of equipment. These aren't hard and fast rules. Generally, we defer to the OEM to recommend what their machines can handle. Oftentimes, engineering companies or end users will specify a certain amount of runout that the machine needs to be below before it gets shipped to site. But even just as a kind of a rule of thumb here, using that ISO recommendation, the 25% of the alert limit, as an example here, if the alert is at 6 mils, then the runout should be less than 1.5 mils. Ideally, we want it to be as close to 0 as possible, and you should always check with the interested parties to see what their preferences are or what the tolerances are for runout. But in the absence of those, fixed values, these are some guidelines that you can use for assessing how good your runout is. And now that we've measured the runout and identified it, what do we do with it? Well, how do we mitigate it? If you've measured the runout and have determined that it is too high to live with, there are a couple of things you can do. If you've narrowed it down to being primarily mechanical runout, this can be removed by putting the rotor in a lathe. Perhaps that second point should have been up front, but we would definitely recommend using an expert lathe operator. They can assess what the best way would be to mitigate that. One consideration might be to use B-blocks to support the free end of the rotor to ensure that the runout's removed so that you don't have any errors induced by a lathe or by a faulty lathe. That might be a consideration there. But once you do that, once you've done a pass on machining it, perform a new runout test using the same sort of reference material or reference points and be able to compare it and show that you have improved the situation there. If you have determined that you've gotten mechanical and electrical runout, we always recommend doing the mechanical runout first. Different variations or different ways of machining can potentially induce some electrical runout effects. So you want to make sure that you've got to take care of the mechanical side of things first before you take care of the electrical aspect of it. And to mitigate electrical runout, you can burnish the shaft. Again, work with an expert lathe operator to make sure this is done properly. If done improperly, it can make things much worse before they get better. And you may need to even look at degaussing the shaft. And again, once you've done both the mechanical and the electrical runout or removal or improvement, make sure you perform a new runout test at the end to make sure that you've addressed the issues that you identified. But what about while the shaft is in the field? If the machine is operating and you suspect that you might have some vibration issues or you need to do some other sort of diagnostics, it's not always practical or possible to take the machine out and fix the runout. So you still need to be able to do something with that information. So that's where the diagnostic software like our Adre software or System 1 gives us some tools. So as we established, when the machine is at slow roll and there's no dynamic effects operating on it, any signal that's there is what we would consider runout, the total indicated runout. And we can then use that signal and we can compensate for it. We can make the assumption that at slow roll there should be no, quote unquote vibration. And this is what we call our slow roll vector. So in this particular example, we're using the 1x vibration. So we can say that there's a slow roll vector there that in this polar plot, it's obscuring the real data. And we want to be able to compensate for that or subtract that slow roll vector. So we look at the data, which would be the red trace. The raw data would be the red trace there for a startup or shutdown here. And we can take that initial vector and we can subtract that vector from all the values. And visually what that does is it moves that same trace, that same startup or shutdown polar trace, and starts it at the origin of the polar plot. So in that case now, when the machine is at, quote unquote slow roll, in this case here, it looks to be about 2,740 RPM, we can now say that we've compensated for that slow roll vector. And everything else beyond that is purely as a result of the vibration on the machine, any sort of dynamic effects on that machine. And System 1 and Adre and others, they will also in the plot tab there, they'll record the slow roll vector. So in this case, the slow roll vector is 1.696 at 165 degrees. This is useful information, not just from the fact that we know what we deleted, but start after start or stop after stop, you can confirm that slow roll vector. And if the machine is staying consistent, that slow roll vector should stay consistent. However, if that slow roll vector is changing, that can give you other indications of potential sources of error. You know, maybe it's a shaft bow that's changing as the thermal effects of the shaft happen, or maybe it's something else. So, you know, slow roll is not always just something that you want to get rid of or want to delete. It is something that you want to make note of and can potentially be a very useful diagnostic piece of information. Again, using that same data set, here we show that same information as a Bode plot instead of a polar plot. And once again, you can see that at the origin there, at the start, the slow roll speed of around 2,700 RPM, we can take that and we can bring it down to 0. However, it's important to note that although a polar plot compensates very visually, it compensates very nicely. The whole trace basically it's kind of shifts to the origin. Bode plots are a little stranger to try and mentally do that shift. So it's helpful to have the software do it for you. But the important thing to note here is that it can do it for you, and then when you do compensate for the slow roll, there will be a note there what the slow roll vector is that was used for that compensation. As we wind down here, I wanted to address a couple of frequently asked questions or gotchas that I often see related to Runout. A question that's often asked is that, well, if we can measure the size of the defect or the amount of the runout, can we just remove that amplitude from the overall? Can we basically just mentally compensate for it that way? And the answer is no, not really. The defect or the runout may or may not add to the overall amplitude. If we simplify things down, just for an example, to just the 1x frequency, the 1 times the rotative speed frequency. If we look at the 1x vibration, it's going to have an amplitude and a phase. And if we look at the runout, it's going to have an amplitude and a phase. All we can really do is we can add those two vectors. And depending on how those phases relate to each other, they could either add together and you could exaggerate the overall vibration level, or they could subtract from each other and artificially reduce the overall vibration level, the indicated vibration level. So just being able to take that amplitude of the runout and just subtract it is not something that we recommend. Even just visually here, just looking at something small like a scratch, depending on how it relates to the vibration in terms of phase, that scratch could artificially add to the overall peak-to-peak amplitude as it looks there in the Y probe. You can see the point of the scratch artificially adds to the amplitude, or it may be masked by the actual vibration there, as in the X probe there. So you see the tip of that scratch doesn't really add to the overall peak-to-peak amplitude of the vibration signal. So depending on the defect and depending on the phase, the effect may or may not add significantly to the overall amplitude. So just simply deleting it or compensating for it like that is not really possible. As we discussed already, there are ways to compensate for vibration in the software from a diagnostic standpoint. So there is value in that. But when we do it in the software, it's going to be much more intentional and much more specific. So we're safe there. But for the purposes of protection, and particularly in our protection monitors like the 3500 and the 3701 and Orbit 60, we do not offer the ability to compensate for that runout in the monitor itself for protection purposes. And also a note of caution about plating. Occasionally a rotor is refurbished by plating the bearing journal area to replace worn material. Sometimes the surface will be intentionally roughed up to allow the chrome plating to adhere better. However, the probe will see through the plating to the rough surface underneath, resulting in runout, although you may not see anything visually on the outside. Also, chrome plating has very different electrical properties than typical shaft materials and strongly affects proximity probe output. In general, plating the area of proximity probes is not recommended. However, when this is not an option, plating thickness should be at least 20 mils to prevent the see-through effect mentioned above. And the proximeter sensor should be calibrated to the plating material rather than the substrate shaft metallurgy. In conclusion, the best way to fix runout is to prevent it in the first place. By taking due diligence during all stages of manufacturing, machining, shipment, installation, you can ensure that the target material that the proximity probe is looking at is going to be as good as possible. From making sure that the material is of good quality, making sure that the machinist knows what they're doing with that material, making sure that the lathe is in tip-top shape, making sure that the tools are sharp as possible, making sure that all the right processes are followed, even going into the shipment side of it, making sure that the probe target areas are properly wrapped and protected so they don't get rusted. And the installation side of it, making sure that the right tools are used when barring the machine over or rotating the machine so that probe surface area isn't affected. All of this works together and the details matter. We're fighting for microns and millivolts when we're looking at vibration here, and every little bit helps. I hope you've enjoyed this overview of runout and how to identify it and how to mitigate it. I'll also note here that we do have a couple of orbit articles that we can email to you. Please reach out to your local sales manager or to either myself or John, and we'd be happy to send those articles to you. Or if you have any questions, we'll now jump to the Q&A where we'll address them.
Okay, we are now at the Q&A portion of the program. If you haven't already, please type your questions into the Q&A panel. If you need to leave before we finish the Q&A, please do take the time to fill out the survey that will pop up. Okay, here's our first question. And it is, let's see if I can see this. What are the keys to identity between a mechanical and electrical runout? Derek, can you take that for a moment?
Yeah, sure. Hopefully this was somewhat addressed in the slides there, but just to kind of refresh, the proximity probe with the way it operates, it'll identify the total indicator runout, which is both the mechanical and the electrical together. So that's why when we do shop tests for runout, that's why we also have the dial indicator, which will just measure the mechanical. So if you do the total minus the mechanical, the remainder will give you an indication of the severity of the electrical runout. There are other more specialized tools that can be used, Gauss meters and that sort of thing, to measure electrical runout directly. But that's one way you can identify between mechanical and electrical.
Okay. Next question is, what does it mean if your runout changes between runs? So I'm interpreting this as, people keeping track of their runout values in between runs and having, more than a tenth of a mil change or something like that, which would be in the noise level. So a couple of possible causes for this might be, in the worst case, a shaft crack, where the stiffness has changed and now the rotor can bow more and it'll exhibit a change in the runout. And speaking of rotor bow, if you leave a shaft turned off for a great length of time, it will tend to bow, and that might be the cause, in which case you need to run it for low speed for a little while to run that run out, that sag out of there. Okay. Can Bentley service personnel record runout in a machine shop? Derek, you want to?
Yes, definitely. This is a regular service that we perform. We have the tools in terms of the prox probes and the dial gauges and the brackets and things, and we regularly work with machine shops that when a customer requests having a runout report, we can come out and bring the tools and provide that report for you.
Okay, great. This next question is, you mentioned Bodhi and Polar. Can we compensate any other plots like trends or orbits? Certainly, yeah. In fact, orbit, when you use Adre or System 1, we take what we call synchronous samples, which are timed to the key phaser. And we take a certain number of samples, maybe 128 or 256, it depends upon how it's configured, samples per revolution. And when you do that, and your machine is at 300 RPM versus 3,000 RPM, it's taking it at the same shaft position, so you can do a point-by-point run-out subtraction, and we call that a waveform compensation. Okay. Let's see. You mentioned, does a scratch or crack have to pass directly near the probe to be seen? So I'm going to let Derek take that while I queue up the next one.
Sure, yeah. So for a scratch itself, that would need to pass underneath the probe itself, underneath the probe tip in order to be seen. Cracks can be more internal, and that's, to John's point earlier, those can be a little tougher to diagnose. The changing response for similar conditions, because you're basically the shaft stiffness is changing. You won't directly read it as a sort of a blip in the waveform or something like you would with a scratch, but you will see it as unpredictable or unpredictable behavior or unpredictable changes in the shaft behavior. Oftentimes in the 2x amplitude. That's one of the reasons why we offer 2x amplitude and phase filtering directly in a lot of our monitors, like the 3500, because that can be a leading indicator of a developing shaft crack.
Okay. Will spot heating to correct bow create an electrical anomaly? And my first thought is that yes, it probably will, because it'll change the metallurgy in that area. Derek, do you have anything to add?
Yeah, I think if the heating is done properly and very evenly and slowly and with from an expert, that can be one way to do it, but you do definitely want to be careful, because if you do it too intensely and too focused, you will definitely change the grain structure or the metallurgy of the shaft itself, and that can definitely induce a electrical runout. Yeah.
Okay. Next question is, can you record runout with a digital multimeter? And I'm going to suggest that you're going to be looking at your DC values there. You're going to get a rough estimate of it as you rotate it, but it's probably not going to be as exact as using an oscilloscope or an Adre system. You have anything to add to that?
No, it's in a pinch it'll give you an idea, but it's definitely not as detailed or complete as something like an Adre would be. Yeah.
Okay. Rotor bow, as stated in your slide, what it means. What does it mean? So rotor bow is basically, you think of your rotor as straight, but you've got all this weight in the center between spans. So as that weight affects, the rotor while it's standing still, it will cause a little bit of sag. And as it sags, it causes what we call bow. And I don't have the ability to put a picture up right now, but it's greatly exaggerated look. You can see that the rotor is really not straight at that point. On a steam turbine, we usually use an eccentricity probe to make sure that the the sag has been worked out of the rotor before starting. Okay. Derek, you have anything?
Yeah, and rotor bow it's quite easy to identify in terms of when you're at very low speeds. It gives a very nice sort of circular path. Makes it look like a very nice vibration signal, but your shaft is rotating so slowly that there's no way that actual vibration would be induced. So that's one way you can see or get an indication that you might have a rotor bow. Will show up as a big 1x amplitude.
And to your point, it will be very circular in nature if you look at the orbit. Okay. What are acceptable burnishing methods? And honestly, the only one I'm familiar with is using a diamond burnisher.
That would be what I would recommend as well. Yeah. We do have a little bit on burnishing in one of the orbit articles, but yeah, the diamond tip burnishing is what we recommend.
Enough. With only eddy current probes, how do you create a key phaser? And so eddy current probes are great for key phasers. You would not want to put it in your XY path, but you would basically mill a notch about 2 probe tip diameters in length, and an eighth of an inch deep. Usually we use a ball end mill so that you don't have any stress risers and sharp corners. I have been in the field where we didn't have a key phaser where it was supposed to be, and we actually just kissed the shaft with a drill bit and worked very well. So, okay.
And the key, if I could just jump in, one of the key things that's sometimes difficult to visualize, particularly when we're talking about XY probes, is that if you're looking perpendicular to the shaft, that key phaser probe, that key phaser eddy current probe, will be in a different plane than those XY probes. So the XY probes will ideally see a nice clean rotor shaft, and the key phaser probe will be a separate probe, and it'll see that notch or projection on the shaft.
Great, thank you. And I didn't realize time ran away from me, so thank you for attending today's webinar on identifying and mitigating runout. If you have any additional questions or would like to receive professional development hours, please contact your account manager. If you would like to learn more about using System 1 or machinery diagnostics for that matter, and are interested in attending one of our formal courses, please visit www.bentleytraining.com. While we have begun offering several courses in person, System 1 and machinery diagnostics are still available as online virtual learning. And if you would like to watch a replay of today's session or suggest it to a friend or colleague, you can find a link to it in the related content tab on your console. I will caution you, however, that the replay won't be available until about half an hour from now. In the meantime, the related content tab also includes registration links to our future webinars as well as a PDF of today's training materials. Also, you can always log back in here later to get to the resources tab. Do this by clicking on the link in your original calendar invitation. One last but important thing, a survey will pop up on your console after the webinar concludes. Please fill it out as we value your feedback. In fact, it was because of this feedback last year that we launched these Beyond the Basics webinars this year. So again, thank you for attending and have a great rest of your week.